is it's only 3 days, so we may have not included all the topics. So please, it's your chance now to contribute to the program. And now I pass to Ellie.
Yeah, I'm just going to put the Padlet in the chat. But I will also share my screen, I think. Okay, you should see this now. Now this was the idea of these sessions was just to gather various discussion topics, and for this room it was about stellar binaries and multiples, and we had a few so we'll go through them now, and if we have time we'll see the example there. But so there's like 3 or 4 I think people have put, so you can just we'll spend time on each one basically, and because there's also a session tomorrow on this as well. So you can add to this as we talk. You can add to it tonight or tomorrow morning, because there will be another session. Yeah, so I guess we can get straight into it. And the first one, if I open it, there's no pretty picture for this one. That's we have some text. And who submitted this?
No, sorry, I mean, are we skipping Valeria's first one that's in the Padlet?
It's only because it was an example, so we will the last one.
But it's a good question. Okay, that's fine. Sorry, I missed that. So I'll stop interrupting.
So I guess they're in the call.
Yeah, sorry, I didn't really prepare anything.
No,
I thought we were going to decide which ones we were going to go through, and then I would know. But yeah, just in short, the question is very straightforward, I guess, and it's something we briefly mentioned yesterday, but I feel like I don't have a definite answer. And the main thing I've been wondering is, well, we have maybe 30 verification binaries by now. And the question I have is, one, is that enough? Especially, do we need more in the south? Because they are mainly in the north, and the detection depends on direction, right? So I wonder if we need to look for more in the south. And the second part of the question is, what else do we need to know about the ones that we do know? Do we have all the parameters we need? Do we need to do more observations? I gathered from yesterday that we need to keep following up then to get the P dot, but is there something more we need to do? And the question is mainly to the theoreticians, I guess, but please, everyone, give their input.
So can I also ask, I don't know everyone, and I wish I did. So Ingrid, it says here you're from Warwick, but can you just tell us where you are and what you're saying?
Oh, yeah, sorry, I'm Ingrid Pelissoli. I'm a research fellow at Warwick. This is my second postdoc. Previously, I was in Potsdam working on hot subdwarfs. Okay. So yeah, the main things I work on are hot subdwarfs and extremely low mass white dwarfs and white dwarfs in general as well.
Okay, thanks, Ingrid.
Yeah, no worries.
So this is kind of related to a question I have maybe, which was alluded to yesterday in the pre-EM meeting, but one thing that I don't think I understand, because I'm an observer, is what the actual biases in the sample we have are, right? What are the biases from the way we do the survey? What are the biases from our magnitude limits? What are our biases from the periods that we're able to sample? I don't know what any of those are. And this kind of has that feeling to me that it's relevant to those questions. especially if we're going to try and compare observational samples to what we generate with PopSynth. You know, a good thing to do would be to take the PopSynth models and make the cuts that represent the biases that are in the observational sample just to see what we get.
Well, if you talk about biases, that's probably the most biased sample you can think of.
Right, but what are they? I don't even know, right?
Yes, so it starts already with the sky distribution. They're all in the north, most of them are in the north. That's one thing. Then half of them are eclipsing. That's clearly a bias because that's how we define them. Then all of them, if you look at the HR diagram, lie above where the white dwarf tracks. So all of them are young, hot white dwarfs, at least the primary component. So it's full of biases. It's full of selection effects. And we could probably write that down.
Eclipsing is not biased though.
Well,
It's very
you bias towards higher inclination because of eclipses.
But this is random, so it's okay. It's very.
But we find the sample we find them predominantly when they're eclipsing because that's how we find them in the first place. So that's
Right, but
that's-
that's an easy sample. That's an easy bias to overcome, right?
exactly.
okay.
That's right. And then we have half AMC vans, half double white dwarfs, which is probably also biased because AMC vans are easier to spot, I would say. So it's basically full of biases.
So Ingrid mentioned this, and you mentioned it, that they're all in the north. I mean, in as much as, you know, these things are in the plane of the galaxy, is there really an expected difference between the northern and southern hemisphere of the sky? Modulo where the center of the galaxy is, I guess. But
I honestly don't think so. I honestly don't think so. And even more so, I would say the ones which are close by, they are all over the sky. They're still, yeah. So I would expect a similar number in the southern hemisphere, maybe even more because the stellar density in the southern hemisphere is higher if you just scale by stellar density. So maybe even more in the south. But that's something Black Jam and LSST and Foremost and all these surveys will help. Can I ask a question to Shane, which actually follows really what Ingrid also said? Ingrid said verification systems, we have about 30. Actually, a lot of them are not what I could call a verification system because a lot of them require 4 years of LISA observing to actually get some signal noise ratio. That's not a verification system.
yeah.
Verification system is something when you turn on, you were observed for a few months. Well, we heard yesterday from Tyson, longer than a few months, but you observe for a few months and you get a signal. So what would you actually consider a verification system?
Yeah, so part of this is language. Well, yeah. So let me give you two answers. So the first answer is what we called verification binaries in the older literature is binaries for which we already knew they were gravitational wave emitters and we could see them in telescopes. There's been a concerted effort among some of us to start calling these known binaries as opposed to verification binaries, because the idea of verification is in some sense from an era where we weren't sure we could do the measurement and detect gravitational waves, right? So, but you know, what Tyson said yesterday was interesting, and I hadn't really thought about it much, and I thought about it a little bit last night. And, you know, in as much as we're going to need 4 years of data for all the current known binaries, the ones that will be able to measure on shorter timescales than that are ones that have measurable chirps, substantive chirps, right? So once you get up past the confusion knee and into the region where they're chirping, especially once you move out of the detached ones and into the ones which are, you know, at very high frequencies and probably interacting, those will be able to measure on much shorter time scales, just simply because we can just break the data up and we'll be able to identify it in the data just because it's chirping.
Right. Okay.
So it's in the clean part of the spectrum, or clean part of the band, right? And it's over the low part of the sensitivity curve, so they'll have higher SNRs, right? Yeah.
And so for the non-chirping sources, and maybe that's a question for the pre-EM working group doing that work actually. Like for example, for the 7 minute system and other, or 12 minute, do you think it's better to get your inclination to within 1 degree precision, or is it better to get a P dot within 1% precision? assuming you don't have resources to do both.
Yeah.
That's-
You
okay.
mean, is it better for the observers or better for the gravitational wave?
No,
function?
for gravitational waves, right? Better
Yeah.
for gravitational waves.
I would assume it's better for us to have P dot to 1%.
Okay.
Yeah.
Because that's two very different. That requires different strategies of following them up. I would say.
Yeah. I mean, Tyson should weigh in on that, but I would assume P dot's more valuable because that's the harder one to get out of the data. We're going to measure both polarizations. We're just going to have the two amplitudes, and our
Yeah.
amplitude precision is going to be whatever it is. So getting P dot is all about frequency precision, and that's a much harder search to do, right? That's the one that requires long data sets.
It's actually also easier for us, so that's a good thing.
Yeah.
At least for the ones which are eclipsing. That's
Yeah, that's right. Yeah.
Go ahead. Sorry.
I can try to reply to Ingrid's question because she put my reference on the spot. And if you could share the screen with
This has been shared.
the do you see the paper, right?
Yeah.
Yeah.
Yeah, so the yellow is the orange is the observationally data-driven model, and the dashed is the binary population synthesis. And yeah, so we see some, yeah, we see differences, right? And I can tell that the differences like in this range from just playing around come from different assumption on the chirp mass distribution. So of course the binary, the dashed line has the chirp mass distribution that comes from the VPS code, and the yellow comes from the chirp mass distribution when you assume that the primary follows a single white dwarf mass distribution, and the secondary is we have a few assumptions there, but this specific one is the mass mass ratio distribution should be flat, I think. And those two makes difference at these frequencies where you really start to resolve all of the double wide dwarfs that you input. And then there is a little bit of a difference in terms of the separation or period distribution. So one again comes from VPS, and another one comes from the assumption that double wide dwarfs are born at the separation that follows a power law, and then you evolve them via gravitational wave radiation for a time. Yeah, I mean, assuming that the star formation is constant. So they have very different assumptions as well. But from what I understood from this exercise, at those frequencies, chirp mass makes most of the difference. So at least at where the knee ends, yeah, like a better understanding of the masses would help. At the same time, that knee is
knee ends. What is the period there roughly?
it is always like I think that's like 17-ish minutes to be very precise, like 16 point something. Yeah, so at the end is those distributions, the frequency, the chirp mass, and the distribution of the distances that impact less.
There can also be, so Katie and I looked at that's a very smooth spectrum there. So not only is the kind of cutoff a relevant feature, is when you get down to the final subtracted background, there will be structure in the shape of that orange line as well. depending on the subpopulations in the galaxy. So, if we mix the different types of white dwarfs because they have different numbers, then it'll make, and they have different period distributions because of their evolution, then that orange line won't necessarily just be a smooth curve like that. It'll also have kind of up and down structure to it. And calibrating those is something I've always kind of pondered what we can do from the observational data, because I always feel like we're just making guesses as to what these populations should be at the moment. So
yeah, but in this case, like both guesses are equally, not equally, but they're both likely, and they're both based on totally different assumptions.
yeah, right, sure, yeah. But that classic smooth curve there is just assuming a population of double white dwarfs, right? It's not making any distinctions about the evolutionary trajectories and types, right?
Wait, the dashed line has different subpopulation, right? Because it's binary population synthesis. It's put all together, and the curve is the classical fit from Stas. There is an analytical function that then you can fit, and it is flexible for any sort of shape. Actually, it describes both of those curves. So it's also calculated through this iterative subtraction of bright sources, and then fitted. On top of that, there is a fit for the analytical function. Ingrid, are you satisfied with the?
I think I am. So trying to summarize it, yes, we do need verification sources in the south, but we don't need to worry too much because Black Gem is going to find them, or so we hope. Yeah.
Let's see about that.
We are never going to throw away known sources, so find every known source you can ahead of time.
Yeah, I'm just thinking where to look if I have to focus on the known ones or look for new ones.
For foremost, right? Some of them, they might actually be in the subdwarf catalog rather than the white dwarf catalog. The high state system, they have a very clear, distinct, like helium absorption features, very clear. They look a little bit like a DB, and especially the ones like below 17 minutes, they actually have luminosity. Like HB-Lib, AMCVN, the famous ones, they are all in Stefan's subdwarf catalog. So from foremost to the south, I think somebody should keep their eye open for this kind of stuff.
Oh yeah, no, we are.
Yeah, exactly, and because they don't really show up in the photometric surveys.
Yeah, and we need P dots and masses. Okay.
Yeah, masses are typically the tricky part if they're not eclipsing.
So all the known binaries right now have been found with photometric surveys, so they're being identified based on variability. Okay.
No, that's actually only recently that has been started. Like only Kevin and like the CTF work is photometric variability. The old work was the AMCVNs have been found completely serendipitously by taking a spectrum or finding an X-ray source. HM Concrete was actually identified as an X-ray source first, and then they took spectra of photometry and they found it's a compact binary. So it's purely serendipitously. And
but there's no way to do kind of so I worry a lot. I think a lot about known binaries that don't have photometric variability and how we might identify them. And so it's if I were to just take a sample in the sky and do a color cut, I'll get lots of white dwarfs, but I won't necessarily get binary white dwarfs. So then spectroscopy is the only way to do it.
Yeah, there are surveys that are going to do that, like Foremost, for example. For the hot subdwarf survey, we are trying to get 2 spectra of H stars so we can at least have an idea if they vary or not.
Okay. And how efficient would a survey like that be at identifying systems? I mean, how hard is it to decide, yeah, this is a white dwarf binary with the kinds of observations you're going to do?
It's easy to see if it's a binary, because if it varies, it's binary.
Right, okay.
But it's not easy. We don't get any periods from that. So it could be a very long period binary, for example.
Right. Okay.
So it doesn't give us the whole information, but it at least it narrows down the sample.
Okay.
So there's a hand from Tom.
Yeah, we're free forming, Tom. So sorry.
Yeah, let me just make a quick comment. So as far as photometric variability surveys, this is Northern Sky with ZTF now, but we've now done a periodicity search over all roughly 1.5 billion Pan-STARRS objects. So that's something interesting, because we don't put any a priori cuts on the data using Gaia. We do that afterwards to see where the sources lie. That, it's not spectroscopic selection, but we do have now variability selection for all Pan-STARRS objects. And for instance, we have 10,000 objects with photometric variabilities less than periodicities less than 10 minutes.
Wow.
So the problem now for us is, how do you do follow-up and actually tease out the binaries from everything else that happens with periodicity on scales below, say, 60 minutes.
Okay.
Yeah, so we're just drowned in data once we completed this periodicity search of all Pan-STARRS sources.
So you're drowned in data. What's your strategy?
We don't have a good one yet.
Okay.
So far what we've been doing is pretty much going after high amplitude periodic sources that we haven't, that we didn't go after before. You may have seen our recent Nature paper on candidate Black Widow system, optically identified. We have quite a few other high amplitude variable optical sources, which we do not understand well. So we've kind of gone, at least temporarily, a little bit away from the LISA analysis and more towards other types of objects. We're very interested in EROR-zeta, ZTF cross matches, and we've found now a couple of new polars. And so we're getting interested then in magnetic field evolution and white dwarfs. So, but looking back to the LISA work here, to answer your question, Shane, I think what we need to do is just pound at getting spectra of especially the shortest period objects, because those are going to be the most interesting for LISA, because we call them verification binaries, although I think we should go well beyond just verification and start thinking about the physics of it. But those are going to be the objects that are most have the highest signal noise.
Right. Yeah. We were harping on the verification terminology right before you got in. So
okay, yeah, I had to join a little bit late, and I'm going to have to leave a little bit early. So
yeah, you're good. Lindsay, you got your hand up.
Yeah,
you should introduce yourself because you're probably new to everyone. Yeah,
I was about to say, I'm pretty sure nobody here knows who I am, other than maybe Alexi, because we're on a paper together right now. I'm Lindsay. I'm one of Shane's students. I'm I guess a 6th year grad student at this point, but I come from the electromagnetic world, and now I'm here to have fun on LISA stuff. And Yeah, I don't really know what to say other than I'm Shane's student, so you should just like copy paste whatever that means to you about Shane. Yeah.
I don't know if that's a good idea, but okay.
But I have a very quick question about what you just said, Tom, about like prioritizing which follow-up. So I should have thought of the shorter binaries first. I think that kind of makes sense. And I was wondering if the data is well sampled enough to get a rough estimate on the ellipticity of the orbits. Like, can you tell if they're very circular or if they're just like not like very quasi-periodic, I guess?
Ellipticity is, we have done that with a very small number of sources, basically because eventually to do that well, you really have to get into the details of the timing. You almost certainly need eclipsing sources in order to do that well.
Yeah.
Okay, and I think as far as we haven't done a lot with that at the moment, but to also give people just an example. And by the way, the data is public. There's, there are about 1,000, an average of 1,000 epochs that we have on all Pan-STARRS objects. So, we really have a lot of epochs now. So we can sample light curves quite well. That's why we can do a periodicity search. It's then a matter of, if you will, follow-up. We're very interested in the massively multiplex spectroscopy surveys and what they can tell us about the subsamples of our data. But either way, the CTF data is open to everyone. And actually, if there's interest in other people in working with us on the periodicity data, if you've got good ideas or you've got follow-up capabilities, glad to talk to you.
Awesome. Yeah, I guess as like an initial cut on a large data set, I guess it doesn't make sense to look at ellipticity first. I think that's where I was headed with. Yeah, it sounds like what you're doing with the how close in the binary is makes a lot more sense.
Yeah, so we haven't started on that yet, but I think, we've kind of gotten, we have broad interests in addition to Lisa. And like I said, magnetic white dwarfs are currently of high interest. The graduate student that's working with me now is doing an eROSITA EFEDS field cross-match with ZTF, and is now starting to work with members of the eROSITA team to do a much broader survey. So magnetic fields and white dwarfs are not well understood. So that's one of our current topics. But like I said, if there is interest from the LISA community in our data and starting to work on it, be glad to talk to you about it.
Awesome.
Thomas, you're on screen and on, so you have your hand up.
Yes,
Okay.
I want to be polite and raise my hand. So my question is for Tom. This seems like the ideal targets for SDSS5 foremost. I mean, this is like, for them, it sounds like a lot, but for them, it's just a few extra kind of fibers, more or less. I mean, are you talking to them to make sure to get them?
I've got half the money now for Caltech to join SDSS5, and I've gotten lots of encouragement from Julia and Hans Walter on that.
Okay.
No, that's an obvious one. They have, they're very interested in working with us, to put extra fibers on all kinds of interesting objects. And so we absolutely. So in fact, Thomas, I'm working on this continuously now. And like I said, I've raised half the funding for Caltech to join. So I just need to close off the other half. So. Yeah. So also Kareem El-Badri, if you know him.
Yes, very well.
Is very active in SDSS5, and is joining Caltech, and he's a regular participant. In fact, I'll be talking to him at about 10 a.m. So. But foremost, no, have not done foremost.
I'm in foremost, and I could maybe help out with that. At least tell you which ones are already in our list, if that is helpful.
Yep, be glad to, like I said, be glad to work with it. We've got so much data. You can imagine, 10,000 sources just below 10 minutes periodicity, but there's everything between there and 70 minutes. Say that's easily of interest, and then Black Widows are hour type periods. So yeah, I mean so right now one of our interests is we definitely have a 4-hour Black Widow candidate. Absolutely, we're trying to go after radio and all kinds of other capabilities. Yep, so it's fun. Yeah, let me know if you're interested.
It's always fun, right?
Well, yeah.
Okay, will that be a good chance to move on to the next one in the deck? So I am just kind of going to do them in order. So yeah, I apologize for announcing order beforehand. So next you have this one from the color. By verification, galactic triples. So are they in the pool?
Nicola's not, but I mean,
It's equivalent.
Yeah.
Okay. Would you like to lead the discussion on this one?
maybe. Yeah, I mean that's yeah, it could be, but it's gonna be very short in the sense that like we kind of discussed it a bit yesterday for the pre-EM. So I think like we can directly skip to the next one. However, it's not clear to me how we can indeed follow up on the verification binaries to kind of see if there is a third companion or not.
Timing. I think Eclipse timing is the best bet. We talked about it yesterday briefly.
Yeah, but
What instruments then?
High-speed photometry.
no, but I think that in case we can have like a dedicated like telecon directly with Kevin to check out on that.
Exactly. I think that's a good point. This is one topic, but generally the P-dot follow-up, I mean, that's something we can actually coordinate because, but I have McDonald, which I use pretty much every month with high-speed photometry, and other people have other resources, Hypercam, Ultracam, and so on. So I think that's generally like, right, and third bodies is one thing, P-dot is one thing. So I think that could be a dedicated telecom.
Yeah.
To coordinate that. I agree. Yep.
Great.
Lexi, you have your hand up.
Yeah, more like a comment questions. I mean, like, so we know that triple companions can be on close orbits and very far orbits. I mean, we know binaries which have triple companions at southern EU or something like that. So I mean, like, basically the question is like, how close can it be to affect the, for example, the pre-Lisa observations, for example, P-dot or something like that? Can we? I mean, the question really is like, what fraction of triples will we pick up that way?
In Lisa data alone?
Before Lisa. So I mean, if you try to find signatures of triples or for example variations or something like that, or some other.
Yeah, so with timing, it depends on the baseline you have, obviously, right? If you have a baseline of 10 years, then you can pick up a period of a few years, right? You need at least to cover one orbit. So but very few systems have timing over several years. Most of them have a few years at most. So I think that's what currently limits some timing. Actually, there is a candidate triple out there. This is B407 Vol, which is the 9-minute AMCVN system, where the optical light is entirely contaminated. It's entirely dominated by a G-type star, but it's been found in the X-rays, right? So it's not entirely clear if this is a by chance like alignment or if it's a triple system. I mean, it's a main sequence component. It's not a substellar component, but so that's yeah. So there's
Tom's PhD student James, who was there yesterday, but I don't think he's here today, is working on that one.
Oh, awesome!
Yeah.
Is that a teaser for you found something or not?
He didn't want to say for sure, but so I'm not going to say, but
I'll ask him tomorrow. We'll see tomorrow. That's actually, that would be
please do make him talk.
Because there's nothing in Gaia. We checked. There's no astrometry in Gaia. Anyway, so I think timing gives you, depending on the baseline you have, and then there's not really much else.
So there's nothing special we have to do. It'll just come out from long-term observations.
Well, they're limited to the ones we can do timing measurement, which is the eclipsing ones, which is only a handful.
Okay.
Yeah, I guess then a triple compare has to be on a 1 to 10 year orbit or something, because if it's wider orbit, then it probably will not change much. So
What's the magnitude of the verification binaries in the infrared?
Oh, that depends on. Typically, most of them are hot, but that's what they found in the phases, so they're typically fainter. That really depends. We have verification systems from 14 meg AMCVN itself down to 21st, 22nd.
Sorry, in which band?
In the optical, so then in the I band, probably that's similar, right? So it's all over the place, but most of them on the faint end because they're white dwarf and compact and small and. So.
Okay, we can look at the next. Yes, this is from Maria.
Yeah, so we sort of discussed it a little bit, but again, question to observers: what properties of here I didn't want to specify double wide dwarfs, but of galactic binaries we consider well measured. And well, I'm interested in knowing, of course, more about double wide dwarfs and AMCVNs. And for instance, I have seen quite precise measurement of double wide dwarf fraction. Do you guys consider this like something that is converging to to reality? Yeah, and in general, like what other things we can sort of start taking as an input for us theorists?
I think it might be good generally to put a document together, to put that somewhere in, maybe like a living document. To put
This can be living, like our Padlet can be living document.
Yeah, exactly. Because that depends on the depends on the type of objects. It depends really on the type of object. Yeah.
I wanted to ask Valeria, does this include non-eclipsing systems as well?
Yeah.
Yeah, okay. I'm super interested in this question also.
Yeah.
I don't have answers, but I'm very interested in the question.
Yeah, we ask this question a lot of what do observers think or know, and it's very hard to find it in the literature, right? So a living document would be awesome, Thomas.
And it's hidden, and it really depends, right? Because different people do different things, right? Ingrid does a lot of the AM stuff. I do a lot of the AMCVN stuff. Jan does a lot of AMCVN stuff, right? So it's really depends on the type of object you ask, and different type of objects have different stuff measured. And like for the AMCVNs, if you really look at the population, we really have no idea about the mass distribution, inclination distribution. You have no idea about the inclination distribution unless for the few eclipsing systems. And it's just, it really depends on the object. I mean.
So are there objects that we have some things that we think are well measured. I mean, it also goes to binary pulsars equally.
Binary pulses are well measured in many ways, especially if they have Shapiro delay or something.
But then the selection of the sample is not well defined in this case.
Yeah. So there's a difference between population properties and individual binary, like individual properties for individual systems.
So,
That's two different things.
can we just back up to something you said a minute ago, Thomas? I just want to understand kind of the way you think about it, right? So you said the inclination distribution isn't well known, right? And I think my response to that would have been, you know, something I think Tazo said earlier, which was the inclination is completely random. So when you say the inclination distribution isn't well known, are you saying the biases aren't well characterized?
Sorry, the measured inclinations are not known at all. Obviously, the system will follow a statistical distribution of inclinations. There's no preference either way. But for an system, if you ask me like the inclination for that particular system, unless it's eclipsing, we don't know.
Okay, so you won't have a number or error bars.
I can tell you probably it's not eclipsing and it's not zero, so it's somewhere between 20 and 70.
Right, okay. You sound like
that.
So basically, when I assume random inclination, it's a good assumption.
Right.
That's an example, right? And then
Okay, now I thought you said that most of them are eclipsing. But most of them for which we know the inclination. are
see
eclipsing.
that way it comes again. The detached double white dwarfs, most of the known ones are eclipsing because that's how they were found.
Mhm.
The AMCVNs, that's not how they were found. So the
Okay.
AMCVNs, most of them are actually not eclipsing. There's actually only, Jan, you have to help me. I think there's one AMCVN eclipsing verification system known, maybe less, I don't know, maybe zero.
I think that's
So-
one.
so yeah,
thing.
Yeah, exactly, one can. So again, that comes back to the type of objects. But I think that's generally a good idea to put together like a living document on selection bias, on things we think we know.
Yeah, right. Yeah.
I think that's a good idea, and we all can. The observers, I look at all the observers in this call, can put in some information. Happy to start that at least.
But I guess it's probably fair to say that for all the systems we know the period, or conversely, are there any systems for which we are really not sure about the periods? I guess probably not.
Some of the ultra complex extra binaries have not fully that have ambitious, but yeah, if we are most of the other systems have very well measured periods. That's something we typically know pretty well. Exactly over, yeah, that's something we typically know pretty well.
And do we know many of them? Like, is it the population or it's like a sample
Ultra complex extra binaries?
No,
Few.
no, we know only about 20, if you like.
Yeah,
Right
it's
now.
few.
Yes,
And
is
then
that a
there's-
population or is that still small numbers?
No period.
Okay,
Yeah.
yeah.
And there's yeah.
I think if you want a sample with well-defined selection effects and well-measured properties, you have to go to the LM survey. I think that's
Yeah.
that's the best
Agreed.
one.
I agree.
I continue hearing this from any direction.
Yeah.
Okay. Not very optimistic, this reply.
No, it's not, it's optimistic. It's more like I think it's a good question, and I mean it's hidden in a lot of different papers, but you have to know which papers you have to read. And so I think it's good to put a living document because it's also in the heads of a lot of the observers. So just put it in a living document, and then kind of make it sure it's updated whenever something new comes up. I think that's kind of then where the theorists can go back and look at that.
Can it be a part, like some sort of a subsection or something in the of the white paper, or it's just too
That would be an awesome thing to do because it would be citable then, right?
Okay, so I'm volunteering to start our Google Docs. That's what I want.
That's okay. Hey, if it exists and it's contained, the next time we do the
Let it
update,
dry.
we can put The end, right?
It started, yeah. Just to
That's
point
the
out-
first
Let's
draft,
open
right?
the title.
Well, but it would be good to have like some sort of a summary, sub
So
section.
what's the timeline for the referee report? It's, I guess, a few months or weeks.
Probably September, yeah.
Okay, so that actually might not be unrealistic to actually put something together if I look at the observers in this call, help me put that together. So, I
Yeah,
mean,
but
I'm
that-
anyway a coordinator, so I can't just.
We're going to start working on it, but the summer holiday will slow things down till September. So September 15th, I think, is our deadline. So
Yeah, probably, I'm guessing we won't add like new stuff unless it was explicitly asked, right?
Oh, that's
yeah,
true. But
probably.
that's up to you. And then also September 15th, basically for the European, that's when the Europeans come back from their holidays now, right? That's
They
the-
have left already.
yeah, they left already, and that's when they come back.
Technically,
You left in August. What do you mean you're leaving in September?
Yeah, right.
okay.
I see a few people have added some more slides, so thank you for that. I'll continue going in order though, just to make it easier. So the next one,
No, this, yes.
Yeah.
But, so, yeah, we can do the.
so, yeah. There's also.
This was because we didn't have time to ask questions after the overview talks. I think it was towards the end, where Sylvia was mentioning that what we will be measuring. No, okay, now I remember. There was a slide about we don't know how many double white dwarfs will merge and how many will survive, and this is something that Lisa will be able to answer. So my question was, if Lisa answers, yeah, how many binaries say merge, can we use that knowledge to learn something about single white dwarfs, for instance? Yeah, like the fraction of mergers among single white dwarfs, or the like improvements on the white dwarf mass distribution, or something like that. And I guess Sylvia answered a little bit, but she's not on the call.
The question is, the merger products will be a tiny fraction
Would it be?
compared to single white dwarfs.
Oh, yeah,
Very
compared to single white dwarfs, that's true. Yeah, that's right.
So I'm not sure if you are gonna be able to identify them. In single white dwarfs.
No, not identified, but if I have like if I have a distribution of white dwarf masses, I don't know which of the most massive ones are mergers or not. I guess I don't.
Yes, so there has been work by, I forgot his name. Because the merger the massive white dwarf single star evolution, they are young, right? They have to be young because they come from massive stars. Whereas the mergers are typically old, and there has been work done, I forgot his name, where they show that they find a massive white dwarf population with an old galactic or old orbit, like old population. So they must be mergers. So that's how you can distinguish between single star evolution and merger products, old population versus young population. And they have shown that, they have found that in Gaia data.
Okay, so it's based on the motion.
It's based on the tangential velocity versus, and then looking right where the massive white dwarfs are on the HR diagram, they're like on the lower luminosity white dwarfs because they're
So
smaller.
it's a combination of the velocity and the temperature. Also.
And the
So
temperature.
they
That's-
look young,
They look young, and
but
they're
they're in an old population
exactly.
environment.
That's right. That's right. And so that's how they identify merger products.
And they could identify many, or that's a theoretical study.
No, it's an observational study combined with theoretical study. No, I forgot how many there were. There were quite a few. Yeah, I don't know. It's been a while since I read this paper.
There's a hand from Alexei.
Oh, Alexia, correct.
No, I just wanted to praise Lisa and say that Lisa will tell us about all the emerging white dwarfs, and I think that's super valuable for like so many people. I mean, people, white dwarfs, if you merge them, they can explode. They can sometimes form a nice, I don't know, arc or bore or something, or could form an SDB star for a while. So in fact, the Lisa data will provide rates for example, production of SDB stars, which could be connected to SDB sample, and then therefore that could be pretty much well linked, and that would be useful. But I mean, for thinking about the most massive white dwarfs, it's also good to think that they should not explode. Or if they do some explosion, then it's good to think to like what's remaining there. So it's kind of probably a bit of a modeling in between to make inferences.
Yeah, I mean, zero order you can just count. You count what goes in, right? The detached double white dwarfs. You count what goes out. These are the MCVN systems that you can see. I mean, Lisa will see all of them at the short period. Then you see what's left. Then what's left is the merging white dwarfs, the supernova 1A, and then So, I mean, in the end, you can just count zero, which I think is pretty cool. And we know, like the Acrobores are the remnants of helium white dwarf mergers, and we know pretty well what the space density is of Acrobores in the galaxy. Well, pretty well. We know roughly what the space density is of the
So
Acrobores.
pretty well goes on the list.
Huh?
Pretty well goes.
Exactly. Yes. So exactly. So for example, there was this paper by Warren Brown on the elms, because these are kind of the helium white dwarf progenitor systems, and they say they can explain all the Acrobores with elm mergers, like mergers from the right. So there's a lot of but with Lisa we just have to count zero order.
But you have also the MCVN. Where does it end up?
And they all evolve to longer periods.
Okay, and then you lose them.
In Lisa we lose them. Yeah,
So
exactly.
you have a population that you don't see.
Yeah, in Lisa we don't see them, but we can just say they evolve as they evolve.
But you cannot count them.
No, but that I think but it's important that you count the ones which start being an MCVN, because what they do later on, it doesn't matter too much, right? Because they survive unless there's something else happening. That's true. Like if there's a supernova happening on the way out, well, that's a different story. That's true. But yeah.
But could some AMCVNs also merge and form? Some fraction of them goes unstable, merges and forms another white dwarf single.
Yeah, that has been proposed by, I think Ken Shen, right, has proposed that, and having a nova which then drives the merger. I mean, that should happen in periods where Lisa would still see them, right? That happens at 10-minute orbital period or below. So Lisa would see them. I mean, we could actually, I mean, that's something also we can count. We can kind of count how many are there and then see which, if we lose some, and because we know the evolutionary timescale from accretion rates pretty well. We think we know it pretty well. So yeah, it's true. That's a good point.
Actually, just related to this question, so like, is it possible at all that it would be possible by Lisa to see a white dwarf binary or AMCVN which does something like nova? That'd be really pretty constraining for probably probability small, but
that would be awesome. Yeah,
that'd be amazing.
that would be amazing. I agree.
Okay. There's a couple more, I think, on the list before, or there's 3 more now. So we might, I don't know if we'll get back onto your example, but we'll keep going. I don't know who submitted this one, but it's about triples. I assume it's someone here.
It was me, so I just wanted to. So the thing is that Lisa is very good at measuring p dot. And when Lisa sees wide or binaries, we'll be able to detect through measurement of p dot of binaries the presence of triple companion. How far will it be seen? Because I mean, it's really very, very accurate. So I mean, it would be imaginable that it could be pretty sensitive.
So what are the predictions, Alex? What are the predictions for triples in these compact double white dwarfs?
This is any triple like stellar mass or planetary mass?
Yeah, that's my question.
Well, I guess, well, we know that there are short period SDB binaries, which are post-common envelope objects, which have triple companions on pretty wide orbits up to 1,000 days, 1,000 AUs, and sometimes like between 100 and 1,000 anyways. So I mean, probably something like that happens for wide dwarf binaries as well, but I don't know of any measurements of wide dwarf binaries with a triple companion detected.
Well, as soon as you have a double white dwarf instead of an SDB, you basically don't only see the triple, the third companion, right, the third star. So you don't see the double white dwarf anymore. And so it would be kind of the smoking gun signal is you get a period of frequency gravitation wave from Lisa with a really precise sky localization. And then somehow, I don't know how, you find the triple, you find the inner bind by, I have never really thought about it, but that's interesting. So I think the question here is like, what are the predictions? I mean, what are the predictions for substellar companions? What are the predictions for stellar companions? Everything which doesn't outshine the white dwarfs are actually easier and probably the way to go first. So I think that would be an interesting estimate, like how many M dwarf triple companions, how many substellar companions you expect in triples, because they're the white dwarfs that dominate.
I can add one other point, so that I mean, there is mountain observations that B stars have a very commonly triple companions. I mean, so like before people thought it's starting from all stars that almost all of them have triples, but actually the triple fraction actually is pretty high already for stars of like 4 solar masses. So if you have a white dwarf of like 0.8 solar masses, then it's very likely to have had a triple companion in its past. So it's actually probably could be quite common for these sources with massive white dwarfs.
Can I have a question? So Alex, you said that you measure p dot, and that's how you could tell if there's a outer triple star, right?
Yes, because the
So
third companion will produce.
Based on that, can you say anything meaningful about the outer star or object? Because I assume that like there is a lot of degeneracy on the mass and separation, and height affects the p dot, right?
Yeah, I think the effect would be something like acceleration. So an acceleration leads to p dot dot.
But can you infer anything about the parameters of the outer star based on?
Yeah, I think effectively the acceleration, and that means probably that we could have something related to mass ratios or something like that. Because we would know the time scale. Yeah, I'm not sure. So didn't think deeply about that.
No, because I thought there should be a degeneracy based on the mass and the separation. So,
so maybe it will be some combination of two that will be constrained.
I can add to this second part of the question, what fraction will be measurable by Lisa? So Camila and on the call, and Nicola Tamanini has a few papers on these, on substellar tertiaries, but I mean, their results can be extrapolated to higher masses as well. And there, the fraction, the part of the parameter space that Lisa will measure is at around a few years. Don't remember the lower limit, but the upper limit for the tertiary orbit. I think for this lowest, for the, let's say, exoplanet sort of masses was a few years. And then if you go higher, maybe you are higher to brown dwarf regime, you can get a bit larger periods, maybe up to 10 years in lucky cases. And I guess if we start extrapolating, then you go a bit further. And in terms of the mass, Camila knows better what is the minimum mass that you can detect in this way. And I think that the maximum is any. Was everything I said correct?
Yeah, more or less, yes. So basically, like the work we've done, we have done it for substellar masses, starting from giant planets. So 0.2 Jupiter masses above, and we obviously injected like random population because the current at the time we did the paper, we didn't know exactly like the parameter space of these objects, and we found that it's easier to detect substellar bodies around high frequencies binaries. However, of course, like if you have a perturber that has like a higher mass, such as brown dwarfs, all of them, it's easier to detect compared to the exoplanets. Ideally, qualitatively talking, like if LISA observed for 4 years, we can detect peers up to 4 years, unless the signal to noise of the inner binary is much high. So it's high, and then like you can indeed like infer like a tiny longer period. When Valeria said 10 years, it's because we also did the test for an extended mission. And that's mostly it. So yeah, masses, everything above, well, we injected from 0.2, but like if you can detect like low mass exoplanets only if you have a very high signal to noise. Ideally, like it's above 7 Jupiter masses, something like that.
Do you know if the if the data analysis team, the LDC, are they prepared to is it easy to extract these systems from the gravitation wave data, or is this something which they would miss because it's not right?
That's exactly the thing I was discussing yesterday. Well, I tried to mention yesterday because we have a paper that is almost accepted with the data analysis team exactly on retrieving, fitting like the gravitational wave with a basic template where you assume that it's just a binary, and then when you assume that you actually have a triple system, and there is a bias, of course, in the posteriors, because sometimes like if you do not know that there's a third planet and you fit just a basic template, you do not retrieve the actual parameters of the inner binary. The Bayesian analysis was done just for exoplanets because obviously it's few of them, well, like fewer than the brown dwarfs can be detected, and then the brown dwarfs we did like and we inferred the object that we can detect. But I can share on the chat the link of the paper because we are in a it's minor review, so the version you have on AstroPH is basically the final one. And then there's all of the details for the data analysis part, which I'm not an expert in, so but you can find it there because Michael really explained it well.
Okay, good.
I'm just gonna
I
share.
wanted to mention that one of the biases, right now I don't remember, but if you share the link, we can look it up later. But one of the biases was even like the sky position on one plot. So it was like, I think it's interesting for observers.
Well, the cool thing is if you have a brown dwarf or something like that, which is not too distant, you can try direct imaging and see if you identify the companion. Right.
So the direct imaging thing that was like about my question before about the magnitude of the binaries, because that's the other way of going instead of like TTV. But given that I don't know yet the parameter space of the planet, I cannot like say anything about direct imaging because it depends by the instrument and the angular resolution we have.
Yes, I mean, by that time, James Webb might not fly anymore. It actually will be done by that time. But I mean, I don't know. I can really say, but I think like ELT like stuff, they will be able, like a brown dwarf will easily be in the infrared. It's infrared is the place to look for those, and a brown dwarf, if it's not too far away. I mean, that's something what can be estimated.
Yeah,
The
and if
direction.
you think about science fiction, we could also have formation of planets around double white dwarfs. So if they're forming, they're hotter and
Oh,
they're visible.
yeah. Yeah.
The potential could also be primordial if they're at 10 AU. So I mean, they could fit in the sort of outer disk.
I mean, and that's not really my expertise, but ALMA, like the multi ALMA would have frequencies which would be able to detect this kind of stuff.
So is
Seriously, man.
that or with Alma more than
Not that cold, yeah.
yeah.
That's pretty cool. Yeah, that's
We mentioned the new instrument.
right. Yeah. Well, and did anybody ever think about like stellar companions where they actually the double white dwarf is outshine, because that's actually that's the worst which can happen to us, that we get this beautiful gravitational wave signal from Lisa and we don't find anything because it's hiding behind the third companion. That would be awful. If there's lots of them, that would be terrible. Right? If you have like I don't know, a G-type star and you have a double white dwarf hiding behind this G-type star. Right, a typical double white dwarf, which is not UV bright, which is not X-rays, nothing. It's just hiding behind this G-type star. We would
So
never.
A companion that
awful.
hasn't evolved to a white dwarf yet itself.
Exactly.
see.
Yeah, like a normal sun-like star. That would be awful. That would be worse. If somebody could do this estimate
come on,
and
it'll be fun. You'll totally get a nature paper out of that.
What's
like, I hope that.
in the galaxy? Stellar triples.
Sorry. Yes.
The percentage of stellar triples in the galaxy.
Yeah.
Okay. Next up, there's a question about eccentricity.
I just wrote a few questions, but I think it's maybe fun to discuss as well, because some people believe who simulate common envelope evolution that after the common envelope evolution, your eccentricity does not have to be 0. So I mean, particularly it could be 10 to the minus 4 is very conservative. A few times 10 to the minus 2 is also realistic, some people think. So, well, I mean, and some young systems should retain that. So the question is, well, I mean, if Lisa has a very good P dot, what are the smallest eccentricities it constrain, for example? Like, would 10 to the minus 4 be realistic?
So I recall that on orders of 0.01, I would have to go look at our paper. So Katie and I, we wrote a paper about constraining the models for the LIGO heavy black holes in globular clusters, because their formation channels in globular clusters go through the Lisa band and are eccentric. And in that paper, we had made a statement or referenced a literature statement about that. Let me see if I can.
What you had quoted was 10 to the minus 2, and I just over coffee, I had a similar discussion with Chris.
Oh, perfect. Okay.
Gave the 10 to the minus 2 number.
Okay.
I have tons of doubts about the statement that after the common end that we have. I'm not saying that this cannot happen. I cannot prove the opposite, but I have huge doubts about whether any of the current simulations can give any relevant predictions about.
Yeah.
Without the main reason of which is the following: when we're talking about 3D simulations that can actually tell you something about eccentricity, 3D simulations stop way before you have a clean post-common envelope binary. They probably stop before you even eject really the envelope, but even if you do that, then the star is not completely stripped. It is left with some envelope on top, which on the thermal time scale might expand again. So it is very, very likely that post-common envelope, you have also another phase of stable mass transfer, where you remove the last, I don't know, 0.2 solar masses or 0.1 solar mass remaining of the envelope. So I would doubt a lot any predictions that you can extract from 3D simulations about it.
So Tazos, what if we flip that around, right? If after the first year Tyson walks in and throws down a catalog, which you can get a distribution of eccentricities that are in this range from, right? Will that be useful for constraining or doing better physics for all of these kind of phenomena we're talking about?
So some 10 years ago, there were a series of papers that were talking about potential kicks imparted on white dwarfs of the order of 10 kilometers. And I cannot reproduce now what was the argument, some asymmetric, I don't know what it was, but there were some observational evidence from globular classes. I can dig out the references. So that would be my first guess, that you have something in the later phase that can induce a little bit of eccentricity like that.
How long does it take to circularize? How long would you be able to detect it until you? Because then you need a really recently born if it goes fast.
I mean, how long would it take to circularize this? What I'm suggesting happens a little bit afterwards, right?
Okay, yeah.
So you have the common envelope, you are left with a strip star and a white dwarf, and then in the formation of the white dwarf, you get a small kick.
Okay.
That barely uses something.
Okay. Very well.
And maybe there's a related thing. I mean, like if you have residual eccentricity of 10 to the minus 1, minus 2, I mean, you potentially could have also higher harmonics maybe in the LISA spectrum. Possibly. Would that be measurable?
Well, at those small of eccentricities, I don't think so. So the Peters, right? They'll follow that Peters envelope distribution, right? That GN of E that's in Peters and Matthews. But I don't know that I've ever plotted it for such a tiny value of the eccentricity. But my guess is it's all going to still be very narrowly peaked around 2. But I don't know. That's a good question. We can check that out easily enough. But yeah,
maybe not the better. I mean, if there's a bright source, right? So it might be the signal will be the second harmonic may be proportional to eccentricity, but if eccentricity is 10 to minus 2, it's just 2 dex shift. But if the source is maybe.
Yeah, well, and in fact, actually, so maybe that intuition isn't right, because the simple fact that Lisa can make the measurement means there's some kind of distinction that we're going to draw out of the waveform somehow. And I'm not, in as much as we do all the analysis in the frequency domain, then there must be some harmonic structure we're triggering on. So yeah, interesting. Okay, there's probably a good afternoon of thinking to do about that.
Well, is the LDC, like, is the data analysis team aware of all this? Because whenever they say, oh, the galactic binaries are the easiest you can do ever, it's like it's all simple sinusoids, monochromatic, nothing weird.
Yeah, no. Right now their focus almost always is on P dot and P double dot, right? And so then they don't include eccentricity at all. Yeah.
Exactly, because that kind of stuff is super interesting.
But they care about eccentricity when they look at the LIGO like bolts.
Okay.
For instance, yes, we saw in Ricardo's talk that that was a fully Bayesian recovery. So it can, the same tools can be applied.
Right. True.
They just haven't been applied yet, because we tell them that galactic binaries, or at least when words come circular.
We say that all the time. That's exactly what we say.
That's actually true. Yeah.
It's our fault.
No, so on the positive note, like they are developing tools, and I guess eccentricity, right? There will be key parameter to be included in the waveforms also for galactic binaries, and we will check.
And also what I said back about the cakes, that was probably not even close to be the most likely. So you can have triples, you can have double wide doors and globular clusters.
Mhm.
So for all kinds of reasons, you might have a little bit.
Yeah. Yeah.
True.
Okay, so we should ask Tyson to.
Make sure.
It will still be like, I mean, it's not gonna be sinusoidal, the signal, but it will still be almost monochromatic.
Yeah, I mean, that's probably something easily, if you do in a Fourier transform, you should easily get like a second harmonic, which then would show up. I don't know, I'm not a Kurdish wave person,
In
but
theory, yes, in
naively I would say, right, if it's a little bit off a sinusoid, you get a second harmonic. I don't know.
And then you have a second source.
Sorry?
And then you think that you have a second source somewhere in your signal.
Yeah.
Yeah,
And
right.
if you do an FT and you have a third body, right, you get this kind of splitting. So I mean, in the Fourier space, it's really easy to spot these kinds of things.
But I mean, to Tazo's earlier point, right? I mean, this is exactly why you want to include it in your search, right? If there are going to be lots of reasons that eccentricity might be there and you don't search for it, the current method of searching where you assume everything's E = 0 is just going to fit those two lines as two separate binaries, right? We call that the binary transform, right? It's just going to make any signal look like a sum of single circular binaries.
That's actually true, yeah.
Yeah, it's a big problem.
Yeah, so basically we have to look for not only for binaries individually, but also make sure that we are allowing them to be eccentric and we're allowing them to be triples, right?
Yeah.
Right. Just pretend you know nothing. Assume it could be anything.
That's the way to do it, exactly.
Well, the truth is, I mean, you already see people doing this with LIGO data. Is post facto, after the first catalog comes about, people are going to go back and do all of these kinds of cool
Right.
things. The question is, what did we do the first time, right?
That's right. Yeah.
So we could have time for one more. or-
Yeah. I just thought it up in my chat.
We had this post-tidal interactions.
It's almost the same question, but I mean, the question is actually maybe interesting to some people because the point is that if you have common envelope evolution, then suddenly the core of the star ends up on a very short period orbit, so it didn't have time to synchronize because it's initially at in the star which is not rotating. So like it ends up after the stripping ends up in a state where it's been quickly synchronized. So the point is that it firstly might be happening in real time. Secondly, it might be happening sort of like, I don't know, equatorially, not solid body. And so basically the question is like, can Lisa put any constraints on the circularization and synchronization process? I mean, especially synchronization.
Yeah. So there's probably more work than this about the work that I know about this was done by Bart Willems and Fra Valsecchi and Vicky maybe 10 years ago. I recall that they calculated the size of the effect, and I think they made a statement about whether or not Lisa could measure it, not necessarily constrain it. So that might be the paper that we should look at. Let me see if I can pull it up while we're sitting here.
Really good. And another thing which is maybe related but also quite fun. So imagine there's a common envelope phase, and then the core of the star ends up as a pulsator. So you have a Lisa binary of a white dwarf plus pulsator. How cool would that be? well, pulsating stars might be end up in instability strip. You know, like the white dwarf can be pulsating, for example.
Our wish list is growing and growing and growing.
Yes.
To your question, didn't Thomas Stories also mention for chirping binaries interacting that you can measure the PW, that you will be able to disentangle?
If you have a good distance, yeah.
Yes.
So this is something which probably should go in our pre-EM, pre-LISA EM kind of project, where if you have how good of a distance you need to have that you get a chirp mass from LISA, and then compare the chirp mass to the measured P dot and look for the difference. I think that's the way to do it, right? So if you know a distance, you get the chirp mass, and you measure the P dot from whatever, from timing or whatever, and then you compare your P dot to the predicted P dot from chirp mass, and then you'll see what's the difference. And the difference is tights. Whether this is synchronization tights, whether this is just whatever, I don't know.
So what Thomas mentioned is that you expect from models to have a contribution of 10% of time, so 10%.
There was this
So
paper
that
by,
kind of gives you the precision you need to measure.
Yeah. There was this paper by the guy from Carnegie. Day is getting long. Who did this calculation for the 12-minute system where he estimated. Tony Pyro.
Yes.
Tony Pyro wrote this paper about actually probably 10 years ago, almost 10 years ago, where he estimated about a few percent up to maximum of 10%. But that's actually, I think that's tidal heating, not synchronization, because it's so compact that you get tidal heating. And that's up to 10%. And with our current models, we'll never be able, because there's so much systematic uncertainty in the white dwarf models that we'll never get a precision high enough for the white dwarfs masses to make this measurement before, right? The P dot is very well measured, but the precision on the white dwarf masses is not good enough to distinguish
I
between.
don't think that Thomas Stories was referring to double. She was referring to mass transferring.
Oh, but that's different. They have mass transfer.
Yeah.
That's yeah. So that's something. Yeah. But I mean,
there you can see the effect of that.
yeah, yeah, that's true. But they're also measuring if P dot is harder, because they move to longer periods, and so that's harder. So tight is definitely a big topic, and I think one of the topics we have to wait for LISA, something we can't do before. At least I don't.
I put that link to Francesca's paper in the chat for folks who want to
And
look
so
at.
what did she say? What did they say?
Well, based on the title, they say Lisa will be able to use this.
Oh, good.
So basically, yeah. So that's in. So it's been too long since I've read it. I don't know everything that's in it. So, yeah. Tidally induced apsidal precession in double white dwarfs, a new mass measurement tool with Lisa.
There we go. That's a mouthful.
Yeah, right. So, okay, we're supposed to jump to the other room, yeah?
Yeah.
Okay.
Yeah. We'll leave it there.
Okay. Good discussion,
Thank you.
everybody.
Yeah, thank
Thank
you.
We only made it halfway through our list, though.
Well, we have tomorrow another hour and a half.
Yeah, that's right. Yeah, so don't add to the list.
Right.
You can do 8 in an hour. See y'all soon.
Yeah.
Bye-bye.
And other people were lazy and did not discuss all the time.
What?
Yeah, the group finished early.
Yeah, I saw that. They're like,
We just saying. We had.